Welcome back to Dardres Education. If you watched our nodal analysis video, you know it is a powerful tool, but let's be honest. Dealing with fractions, finding common denominators, and handling supernodes can get messy. Very messy. Sometimes you don't care about the voltage at a specific point. You care about the flow. You want to know how current circulates through the system. Enter mesh analysis. This method changes how you see the circuit. Instead of looking at the dots or nodes, we look at the windows. Imagine your circuit is a window frame. Each pane of glass is a mesh. Today, we are going to learn how to define currents that flow around these windows and use them to solve complex circuits faster than you thought possible. By the end of this video, you will be able to write the solution for a complex circuit by just looking at it. First, a definition. A mesh is a loop that contains no other loops within it. It is the smallest open space in a circuit. Here is the mesh analysis algorithm. Step 1. Identify your meshes. Step 2. Assign a mesh current to each one. Now a pro tip, always assign them clockwise. Why? Because if everyone follows the same convention, the math becomes predictable and we can use cheat codes later. Step 3. Apply Kirchhoff's voltage law or KVL to each mesh. The sum of voltages around the loop equals 0, but here is the twist. These mesh currents, which we will call I1 and I2, are imaginary. They don't strictly exist in one wire, but the real current in any wire is just the algebraic sum of these mesh currents. Think of them as water currents swirling in adjacent pools. Let's look at a simple two-mesh circuit. We have a resistor in the middle shared by mesh 1 and mesh 2. This is the battleground. When we write the KVL equation for mesh 1, we travel clockwise. We hit the middle resistor. Our current I1 is going down through it, but look at mesh 2. Its current I2 is circulating clockwise, which means it is going up through that same resistor. They are fighting. So, the voltage drop in mesh 1 is resistance times I1 minus I2. However, when we move to mesh 2, the perspective flips. Now we are I2. We are the main character, so the voltage drop is resistance times I2 minus I1. Memorize this rule. My mesh current is always positive. The neighbor is always negative. Now you could write out KVL equations for every loop and do the algebra, or you can use the inspection method. If your circuit has only voltage sources and resistors, you can fill a matrix directly by just looking at the circuit. No algebra required. Let's build a 2x2 matrix. First, the diagonal elements. Row 1, column 1, and row 2, column 2. This is the SUM of all resistors in that specific mesh. Does mesh 1 have a 2 ohm and a 4 ohm resistor? Put 6 in the first box. Second, the off-diagonal elements. Row 1, column 2, and row 2, column 1. This is the negative of the shared resistor. Do they share a 4 ohm resistor? Put negative 4 in the off-diagonals. Third, the voltage vector. This is the sum of voltage sources pushing the current. If the current enters the negative terminal and leaves the positive, it is a voltage rise. It is positive. If it hits the positive terminal first, it is negative. Boom! You have your system of equations. Just plug it into a calculator. Let's try a 3-mesh beast. 3 windows, 3 currents, I1, I2, and I3. Mesh 1 top left contains a 10-volt source, a 2 ohm resistor, and shares a 4 ohm resistor with mesh 2. Mesh 2 top right shares the 4 ohm with mesh 1, has a 6 ohm resistor, and shares a 2 ohm resistor with mesh 3. Mesh 3 bottom shares the 2 ohm with mesh 2. Let's use our inspection method to build the 3x3 matrix. Row 1, mesh 1. Sum of resistors 2 plus 4 equals 6. Diagonal is 6. Shared with mesh 2, the 4 ohm, so minus 4. Shared with mesh 3, none, so 0. Voltage sources, we enter the negative of the 10-volt source, so plus 10. Row 2, mesh 2, sum of resistors 4 plus 6 plus 2 equals 12. Diagonal is 12. Shared with mesh 1, minus 4. Shared with mesh 3, minus 2. Voltage sources, none, so 0. Row 3, mesh 3, sum of resistors. Let's say it has a 5 ohm and the shared 2 ohm. Total is 7. Diagonal is 7, shared with mesh 1, 0, shared with mesh 2, minus 2. Now simply plug this into your calculator or use Kramer's rule. The results, I1 equals 3 amps, I2 equals 1 amp, I3 equals 0, 5 amps. We just solved a massive circuit in under 60 seconds. Mesh analysis is your best friend for planar circuits. It turns a physics problem into a pattern recognition problem. Remember the rules. 1. Clockwise currents. 2. Diagonals are sums. 3. Off-diagonals are negatives shared. Next time we will tackle the supermesh. What happens when a current source gets in the way? If this video helped you understand mesh analysis, please hit the like button and subscribe to Dardres Education. We are building the ultimate library for engineering students, and your support helps us keep these tutorials free. Thanks for watching, and happy engineering.